Good morning, everyone. Today, I will be presenting to you our Kaggle competition, New York City Fair predictions. We are Group 33, and the team members are Leong Keng, Wei Ming, Benjamin, and Urshad. The contents of our presentation includes an introduction, our proposed solution, followed by a demo solution, and lastly, our conclusion. First, let's talk about our introduction. New York City Taxi Fair Prediction is a Kaggle competition that is held in 2018. It has over 1,400 teams participated in the competition. In this competition, the participants have to build a model to accurately predict a rider's taxi fare in New York City. There are some key important features provided to help us with building our model. Features such as pickup date and time, pickup and drop-off coordinates, passenger count, and lastly, fare amount. The dataset consists of 55 million training data and 10,000 test data. With all this information at hand, let's talk about our proposed solution. For our proposed solution, we will cover firstly the data extraction, followed by data pre-processing, feature engineering, the methodology used, and finally our model selection. In data extraction, we focus on cleaning of the dataset. To recap, the dataset from Kaggle consists of around 55 million training data and 10,000 test data. Due to the large training data, there were issues with memory spaces as well as slow computation time. Therefore, we extracted only 10 million training data for our solution. Entries that contain missing or NaN values were dropped. After data extraction, we observed several problems from the statistics shown here. The minimum fare amount is negative 44.9. This implies that there is at least one data that contains a negative fare amount. This is an abnormal fare as it meant that the passenger got rewarded for traveling on a taxi instead, and it would not help our model. Therefore, we will drop entries where the feature fare amount is less than 0. Next, the minimum passenger count is 0. This implies that there is at least one data that contains 0 passengers. It could be the case where a taxi was called to a passenger pickup point and was charged a flat booking fee. However, the passenger did not turn up. The other possible reason could be the taxi was transporting goods instead of passengers. Since our problem statement was to estimate the taxi fare for a rider to travel from one point to the other, we will be dropping entries with passengers less than 0. Next, the disparity of latitude and longitude for both pickup and drop-off point is too large, which exceeds the coordinates found in New York City. For example, a proper value for pickup latitude ranges from 40 to 42, but the data is showing a range of negative 740 to 2140. So we will have to filter out those data that are out of New York City. There are also other limitations of the dataset, things like drop-off date time, where we were not able to access the correlation of the trip duration on the taxi fare, and the type of vehicle is not specified. Where based on domain knowledge, certain vehicle types such as premium taxi, limousine, seven-seater vehicle may incur extra charges. In data pre-processing, we will be focusing on removing the outliers from the dataset, or data that is irrelevant. We performed in-depth checks on the fare of each trip. We found out that there were numerous rows of data with fares less than $2.50. These rows were dropped from our dataset due to the fact that the base fare of hailing a taxi in New York City is $2.50. As mentioned before, there were a couple of rows with passenger count of 0 in the dataset. These rows are removed from the dataset because they do not meet the criteria of transporting a passenger. There is a possibility that these trips are deliveries of goods or pets, but we have decided not to include it in our prediction model for consistency. Here you can see a visual illustration of the pickup locations on the world map. Most data points are located correctly around New York City, with coordinates ranging from 40 to 42 degrees and negative 75 to negative 72 degrees. However, there are some outliers identified in Spain and in North Pole, all of which will be dropped from the dataset. We used a bounding box to remove those points outside of New York City. However, do note that in order to cover the whole area, the bounding box was adjusted based on the length and breadth of New York City, and since New York City isn't a square or rectangle shaped region, some coordinates outside of New York City will remain in the data frame. This is a limitation of using bounding box. Before further exploring the dataset, a baseline model was trained by using the linear regression model. It was trained with all the features in the dataset, producing a root mean square error of 8.53. Which should be the worst score from now. This will be a benchmark RMSE value, and any model that was trained after should achieve a better or in case a lower RMSE than the one from the baseline model. Now we will introduce our feature engineering. There are 4 main features we did for our feature engineering, starting off with distance and time, which should affect the feature fare amount based on domain knowledge, followed by possible features such as traffic density and passenger count. Some of these features do not exist in the original data frame, thus we perform feature engineering using existing features in the data frame to generate them. We will elaborate on how these features were generated in the next few slides. First, we have distance. We generated the distance by finding the absolute difference of the latitude and longitude between two locations. Then, we convert the differences into miles. One longitude degree is equivalent to 50 miles, whereas one latitude degree is equivalent to 69 miles. Finally, we calculate the equivalent distance between 2 points. Since the Earth is not flat, we have to further calculate the actual curve distance with trigonometry functions. After calculating the distance, we found out that there were a number of distances which are less than 50 meters. While there is no minimum distance rule for taxi trips in New York City, it is not representative of a real taxi trip and could be just noisy data, or a to and fro trip. Hence, we will be removing these entries out of the data frame. After calculating the geodesic distances for every fare in the dataset, they were used to check for correlation with the taxi fare. As seen in this picture, there is a moderately strong and positive linear association between the fare amount and the distance traveled by the taxi. However, you can still see a number of data points which showed high fares for short travel distances and low fares with long travel distances. Therefore, we decided to explore why we had such a distribution. So, we created another feature called fare per km, which computes the fare rate per 1 km of distance traveled. We plotted three graphs: fare amount, fare rate per km, trip distance against hour of the day. Here, we can see a correlation between fare amount and trip distance, where long-distance trips generally translate to a higher fare, vice versa. On the other hand, we can see that for the fare amount per km graph, there is a gradual increase from morning to evening, which might indicate some sort of surcharge based on timing or location. However, there seems to be no extra charges for long-distance trips since the fare per km remains the same and was at its lowest point apart from Monday and Saturdays. The fare per km only increases from 8 am to 6 pm. Based on domain knowledge, 8 am to 6 pm is the standard working hours and it could be the fares increasing because there is more traffic in the area, resulting in longer traveling time. The short distance could be just riders going to workplaces, which could be a few blocks away. The fare increase could also be attributed to some surcharge when visiting a certain location. We continued to investigate why does the fare per mile only increase from 8 am to 6 pm. With the limitation of the amount of features that we have, we try to infer if passengers traveling during that time frame did face heavy traffic in the area, resulting in longer traveling time. We plotted three graphs based on the data we observed from the fare per mile against the times of day graph. We picked 3 days, Monday, Wednesday, and Friday. Wednesday had the highest fare per mile across all the different days, while Friday had the lowest. Based on this data, we can see the traffic density on each hour of the day. From the density plot, we can see that it's generally true that traffic starts to populate at 8 am as seen in the first two plots of Monday and Friday, Wednesday. However, the taxi density across all 3 days continued to increase up till 10 pm. This contrasts with the fare amount per mile visualization as it showed that it starts to decrease after 6 pm. In addition to that, we can see that on Sunday, the traffic density at 12 am to 2 am is quite dense, but when we observe the fare per mile graph, we can see that it was at its lowest point. Based on this information, we can infer that the traffic density and traveling time has a low correlation with the fare amount. Instead, it may have a high correlation between the time of the day, perhaps due to certain surcharges according to the time of the day. From the previous findings, it seems that the fare amount might be affected by the time domain. With the given pickup date time feature in the dataset, we were able to extract the year-month days of the year, days of the week, hour and time as features, and plot each of them against taxi fare amount. Based on the graph visualized, we can see that the time domain plays an important factor. Here are some of our observations. The average fares increased over the years. The fares in September are the highest but lowest in January. The average fares are highest on just Sunday but lowest on Saturday. The 5 am to 6 am timeframe contributed to the highest average fare in a day. So, we can conclude that the year, month, and the hour of the day affects the fare amount of the taxi. Lastly, the correlation between the passenger count and the taxi fare was explored. There's no fixed pattern between these two features, indicating a weak correlation and that the type of vehicle may not affect the taxi fare directly. Hence, the passenger count feature can be excluded when training our final model. Next, we will talk about the methodology used to train our dataset. There are two different methodologies used. First, we use the k-nearest neighbor algorithm, followed by the light gradient boosting machine framework. The first model we use is the KNN model. The KNN algorithm is a supervised machine learning algorithm that can solve regression problem statements. We input four features, which are pick up latitude, pick up longitude, drop off latitude, and drop off longitude into the KNN model. Having four input features may not sound good at first, as adding a new dimension may create another opportunity for points to be further apart and affect the KNN ability to make valuable predictions. However, we have enough data density for a 4-dimensional KAN model. The 4 features that are selected have close ranges of value, making it easier to group the data points together. Using the KAN model, any test input which has around the same pickup and drop-off location will have similar fair amount. The second model that was used is a light GBM model. Light GBM is a gradient boosting framework based on decision trees. It makes use of the gradient descent, leafwise tree growth algorithm, which is an iterative first-order optimization algorithm used to find the local minimum or maximum of a loss function. Then it iteratively calculates the next point in the graph using the gradient of the current position, then scaling it by a learning rate and subtracts the obtained value from the current position. When it comes to tuning the hyperparameters of the model, there are 4 categories that affect the model: structure and learning of the decision tree, training speed, accuracy, and combating overfitting. Most of these hyperparameters overlap each other when it comes to categories listed above, which increasing training speed may result in the loss of accuracy. Generally, the main important parameters of a leaf-wise tree like LGBM is the number of leaves, minimum data in leaf, and the max depth of the tree. We then plot the feature importance chart to deduce the important features. We have identified distance to be one of the more important features, and it should help us to train a more accurate model. After comparing both models, we have selected our final model to train our dataset. We have decided to use both the KAN model and LGBM model. After training both the model, we will apply example learning in the validation set. We aggregate the predicted fares from each respective model with different weights. Rather than assigning an equal weight to the predicted fare, we will iterate an alpha value ranging from 0 to 1 and observe the best alpha that results in the lowest RMSE. The same alpha value is used in the test data to compute the final fare amount. Next, we will show you the results achieved for our demo solution. In the KN model, we will first obtain the best number of neighbor by iterating value of neighbor ranging from 16 to 36 with the interval of 4. As observed, the best value of k is 20 in this case. Therefore, k value of 20 will be used in the KN model to achieve better accuracy. Next, in the LGBM model, we train multiple models sequentially, and for each new model, the model gradually minimizes the loss function using the gradient descent method. When it comes to tuning the hyperparameters of the model, the main important parameters for leaf-wise tree like LGBM is the number of leaves, minimum data in leaf, and the maximum depth of the leaf tree and learning rate, where the number of leaves controls the complexity of the tree model, and the max depth of the tree controls the overfitting and underfitting of the model. The learning rate controls the step size, which influence the performance of the model. Ideally, a lower learning rate provides us with a more accurate training model. With all that being said, after training an LGBM model, we achieve a RMSE score of 3.499. For our example learning solution, an alpha value is iterated from 0 to 1 a total of 100 times. The alpha value represents the weight of the predicted fare amount from each model. In every loop, the predicted fares from each models will be aggregated with different alpha value. The combined fare is then compared with the validation set fare amount. The best alpha value is the one that produced the least RMSE. With that, the best alpha value is 0.13. We take 0.13 of the fare predicted with KN and 0.87 of the fare predicted by the LGBM model. The result of the combined fare will be submitted to the Kaggle leaderboard. With ensemble learning, we were able to achieve our best Kaggle score result of 3.022 compared to just using the KN model or LGBM model. We managed to rank 258 out of the 1,485 teams, achieving top 15 to 20% of the leaderboard. Before we achieve our final score, we observed that the added features such as distance, year, month, day, and hour indeed improve the prediction accuracy. Before feature engineering, our Kaggle leaderboard score is 3.49. After adding the distance feature, our score improves to 3.43. After adding the year, month, day, hour, our score is 3.02. Therefore, this shows that this feature does have a correlation to fair amounts. Finally, to conclude our presentation, we have faced various limitations and difficulties while carrying out the project. Firstly, there are memory limitations. The dataset that was provided had 55 million entries, which was way too large to be read by the Google Colab notebook. Secondly, we had a tight time constraint due to long training data on a large dataset. This project has taught us the importance of time management as well as useful skills that can be applied in machine learning. As training the models with huge datasets requires a significant amount of time, planning out our agenda in advance is necessary for us to complete the project. We have also learned the importance of every step taken in this project, the cleaning of dataset, methodologies that were applied, feature engineering, and feature importance. All are all necessary to help us derive a model that performs well. That marks the end of our presentation. Thank you.